Hello and welcome to our lesson on parabolas. This is going to be from section 10.2 in our Precalculus text. In this lesson, we're going to cover everything parabola related. So what you see in front of you are all of the formulas that you're going to need to work with parabolas. I'm going to go through and identify some of the key components, and then we're going to go look at a DESMOS window to give you a visual representation. And finally, we will look at some examples to see what you're going to be expected to do. So in this information chart, all related to parabolas, the first thing I want to point out is the axis of symmetry would be the line that cuts the parabola down the middle. And if you have the x portion squared, that means you will have a vertical axis of symmetry. If the y portion is squared, you will have a horizontal axis of symmetry. Okay? So if you have a vertical axis of symmetry, the parabola will either open up or down depending on the value of p. If you have a horizontal axis of symmetry, the parabola will open either left or right. So we do have given the standard form of the equation of a parabola that opens up or down, and the standard form of a parabola that opens either left or right. I would like you to notice that the vertex for either type of parabola is the same. They are both the ordered pair h, k. And notice that h in either case is the value with the x variable, and the k, again, in either case is the value with the y variable. For a parabola that opens up or down, the focus will be the ordered pair h, k plus p. And notice the directrix is similar. It is going to be y equals k minus p. So both of these values have the y portion varying based on the value of p. And for a parabola that opens left or right, the focus will be the ordered pair h plus p comma k. The directrix x equal h minus p. And maybe here you can see that for this type of parabola, it is the x component that varies. And I highly recommend, if you haven't done so already, that you pause for a second and write down these formulas because they're going to be needed in your notes. All right, so going to DESMOS, we're going to explore the parabolas. First, we're going to start with the ones that open up or down. Here, maybe you can see that I've got the standard form of the equation of the parabola input. And the way that I have it set currently, it is opening up. Notice that the vertex is at the origin. This list of variables here, these are my sliders or the components for h, k, and p. And we will adjust these to show you how the parabola changes. So remember we said that h is the value attached to the x. So if I change the value of h, it should change the value of x. So notice if I slide this to the right, we're going to have a shift to the right. And if I go back to 0 and move into the negatives, that's going to shift to the left. So the value of h is going to be the translation that shifts the graph left or right. K, since it's attached to the y, should shift the graph up or down. So as k increases, we go up. Going back to 0, if we move into the negatives, k goes down. And so this is our vertical translation. The value of p, since it's the coefficient of y in this case, should change the amount of curvature. So if p increases, notice the parabola gets flatter, but then as p decreases, it gets skinnier. And notice that this correlates to our information chart. Notice when P is positive, our graph opens up, but as soon as we go negative, we see that the graph opens down. So this N varies the point on the parabola that I'm going to use in just a second. All right, so if we open up the folder and look at the vertex, you'll see that the vertex is the ordered pair h comma k, like our information sheet says. And if I turn that on, you can see that the vertex is the center point of the parabola. It's going to lay right on the axis of symmetry. Now the vertex, if the graph opens up, would be a minimum. This would be the lowest point on the graph. But if the graph opens down, if I could change that real quick, now see the vertex is at the hilltop, so the vertex would be a maximum in this case. So the vertex can be either a maximum or a minimum depending on whether the parabola opens up or down. Next, the focus from our information chart, h comma k plus p. And if I turn that on, it will tell us the location of the focus. And that point does vary as the curvature varies, okay? So now I think I said previously that the focus and the directrix are related. The directrix for a parabola that opens up or down is y equals k minus p. If I turn that on, you're going to see the directrix. And what I want to mention is that the focus and the directrix will be equidistant from the vertex. So you can see here our vertex is currently at the origin. It's 2 units up to the focus, 2 units down to the directrix. And again, as the value of P changes, you're going to see even if it goes negative, the relationship between the focus, the vertex, and the directrix. Oh, I think one more thing that would be nice to mention is that the directrix for a parabola that opens up or down is always going to be a horizontal line, and the directrix in either case will always be perpendicular to the axis of symmetry. Now the axis of symmetry will be x equals h. If I turn that on, you're going to see that the axis of symmetry is indeed perpendicular to the directrix, and the axis of symmetry also contains the vertex and the focus. So if I could maybe adjust that back here where you get a good look at that. Again, the axis of symmetry here cuts the parabola in half. It contains the focus, the vertex, perpendicular to the directrix. Now, one of the other components of a parabola is the latus rectum. And the latus rectum here, complicated formulas in DESMOS in order to demonstrate what it is. So I'm going to turn that on. I want you to notice here, as I adjust the graph, that the latus rectum always contains the focus. So no matter as we adjust the curvature, the focus changes. Do you see the focus always lays on the latus rectum? So what is special about that? Well, the latus rectum is always perpendicular to the axis of symmetry. It will always be parallel to the directrix, and it contains the endpoints of the parabola that are at the same height as the focus. So even if P goes negative, you're going to see the latus rectum again going from side to side on the parabola, always through the focus, perpendicular to the axis of symmetry, parallel to the directrix. All right, so the last thing that I'd like to discuss about the graphical representation of a parabola, and actually what makes a parabola special, you'll notice that I've turned on the lines here that connect the focus to a point on the parabola. and then from that point to the directrix perpendicular to the directrix. So what makes a parabola special is that the distance or the length of this orange line from the focus to the point on the parabola is always the same length as the orange line connecting the point on the parabola to the directrix. So again, let's open that up so you can see the special relationship here. Notice the distance from the focus to a point on the parabola given by this value is always the same as the distance from the directrix to the same point. And I'm going to change that point as we drag that along the parabola. Notice that the distances are always the same. Coming in, coming in. There's another view right there. And then as we get to the vertex, you will see that those are identical. Now, let's talk about the parabola that opens either left or right. Here we have our standard form of the equation of the parabola. We have all of our sliders listed again. H, since it's with the x, is going to slide the graph left or right. So H changes the horizontal translation. K changes the vertical translation. P, again, changes the curvature of the parabola. And you can see that if P is positive, it opens right. As soon as P goes negative, it opens left. So we can see that characteristic demonstrated in DESMOS. And again, this value of n is just a slider that will adjust a point on the parabola. So taking a look at the vertex again, if I open that up, you're going to see that it's h comma k. And if I turn that on, again, you can see the vertex is at the center of the parabola on the axis of symmetry. So the distance from the focus to the vertex is the same as the distance from the vertex to the directrix. Turning on the axis of symmetry, again perpendicular to the directrix, and the axis of symmetry contains the vertex and the focus. And the latus rectum again, going through the focus, perpendicular to the axis of symmetry and parallel to the directrix. So again, if we change the curvature, we can see how the points change. And we can also change the location of H and K and see how that affects the location of the parabola, the directrix, the focus. All of the information can be demonstrated here in our DESMOS window. And important to note one more time that the vertex, h comma k, the focus for a parabola that opens left or right, h plus p comma k, the directrix, x equals h minus p, the axis of symmetry, y equals k. And again, remember that special relationship I mentioned, depending on where the point is on the graph, the distance from the focus to the point on the graph, whatever that is, will be the same distance as the point to the directrix, perpendicular to the directrix. And that should cover all of the key components for the graphical representation of the parabolas. Now let's talk about what you're going to be required to know how to do as it relates to parabolas. So the first thing is we have equations of parabolas that can be in either standard form or general form, and you will need to know how to convert back and forth between these two forms. Also, if you are given the equation of a parabola in either form, you may be asked to find the vertex, focus, directrix, axis of symmetry, those components of the parabola. and vice versa. If you're given a combination of these components, say the vertex and the focus, then they may ask you to find the equation of the parabola in either standard form or general form. So this is a general overview of the things you might need to know how to do when working with parabolas. And now let's look at some examples. For our first example, I thought we should start super basic. So we're going to start with the quadratic x squared equals y. This is a parabola written in standard form. If they were to ask you to convert to general form, all you would need to do is subtract y from both sides because general form has to be equal to 0. And given this equation in standard form, let's find all of the information we can. So the first thing we want to do is go to our information chart and determine whether we have a vertical axis of symmetry or a horizontal axis of symmetry. We need to figure out which column of formulas apply to our problem. And that's not hard because if you're given the equation in standard form, you simply need to know, is the x squared or is the y squared? In our case, the x is squared, so all of the vertical axis formulas apply to us. So then the first thing I'm going to do is I'm going to rewrite the standard form of the equation of a parabola underneath my equation, and then I'm going to determine the values for h, k, and p. Okay, so here's my standard form equation, and then just to ask you a couple of questions, what would h have to be for this set of parentheses to simplify to only x squared? Well, that would indicate that h would have to be 0 because x minus 0 is just x. And what would k have to be for this set of parentheses to simplify to only y? And that answer is also 0 because y minus 0 is just y. And I don't know if you noticed, but once I know h and k, I can get the vertex. Remember, in either case, whether it is a vertical or horizontal axis, the vertex is the ordered pair h comma k. So we can see that our vertex here would be at the origin. And then to determine some of the other components, we're going to have to figure out the value for p. So in our equation, we can see the coefficient of y is 1. That has to correspond to the coefficient here, which is 4p. And knowing that information, we can come down and say that 4p must be 1. And then we can solve for p. Dividing both sides by 4 is going to give us p is a fourth. And then once we know the value for p, we can find the focus and the directrix. So scrolling back up to our information chart, we can see the focus is h comma k plus p. The directrix is y equals k minus p. All right, so I've got my formulas for my focus and my directrix written down. All we got to do is a little plug and play to get those pieces. So h is 0, k is 0, p is a fourth. And so then we need to simplify 0 plus a fourth to get our y component of the focus. 0 plus a fourth is a fourth. And so our focus would be the ordered pair 0 comma 1/4. The directrix, replacing k with 0, again p with a fourth, and then simplifying is going to give us the equation y equals negative 1/4. Next, finding the axis of symmetry in our case would be x equal h, and in our problem h was 0, so the axis of symmetry is going to be the equation x equals 0, which I don't know if you realize this, but that is the y-axis. And one other piece of information that we could find here is whether the parabola opens up or down. That depends on whether p is less than 0 or greater than 0. So if p is positive, that means that the parabola opens up. And after everything we found so far, I thought it might be fun if we also found the endpoints of the latus rectum. So I think I may have mentioned earlier that the latus rectum is going to be parallel to the directrix. And in our case, we know the directrix is a horizontal line. So that means that the latus rectum is going to be at the same height as the focus, and that indicates that y would be a fourth. So what we want to find is we want to find the ordered pairs on our graph that have a y coordinate of a fourth, which means we're going to come back to our equation and we're going to replace y with a fourth and solve for x, and that will give us our endpoints of our latus rectum. So here we go. X squared equals a fourth, replacing y with a fourth. And then if I take the square root of both sides, the square root of a fourth is a half. But remember, when you take the square root of both sides, you do get a plus and a minus answer. And so this would give us endpoints of the latus rectum to be negative 1/2, 1/4. Remember, the y value was a fourth that we plugged in. And positive 1/2, 1/4. That would be the endpoints of the latus rectum. And let's go ahead and sketch a graph. So we've got our vertex at the origin. Our directrix was y equals negative 1/4. So if I come down here maybe and say that this is negative 1/4, the directrix is usually represented by a dotted line. Remember, the focus is the same distance from the vertex as is the directrix. So then if we come up to positive 1/4, we would have our focus. I'm going to label that focus, label him vertex, label him directrix. And do you see that does correspond with the ordered pair we had for the focus at 0 and a fourth. So we know that the parabola is going to open up. It has to enclose the focus and open away from the directrix every time. And let's go ahead and plot the endpoints of the latus rectum, and that'll give us 2 points on the parabola to indicate the amount of curvature. So if this length that I've designated so far is a fourth, then a half would be twice as far. So this would indicate a half, and this would be negative half. And the endpoints of the latus rectum should go there, indicating that our parabola will open up like so. And there is the best first example I can think of to give you to demonstrate all of the stuff you might need to know how to do if you're given the equation of the parabola. All right, next example. Here we are given an equation of a parabola in general form. I can tell it's in general form because it's equal to 0 and I don't see any sets of parentheses. Now the first thing again we want to do is we want to determine whether this is a parabola that either opens up or down or left or right. We can tell that by looking at which variable is squared. Here we have y squared. So if we go back to our parabola information sheet, we can see that when y is squared, we're going to have a horizontal axis. All of the formulas in the second column are going to apply to our problem. So the first thing that we probably want to do is to convert from general form to standard form, because once you're in standard form, you can find h, k, and p, and from there you can find any information you want to find. So what we're going to do to start with to get to standard form is we're going to group our y's together. Since there are 2 y terms, we're going to need to complete the square so that we can factor that as a perfect square trinomial. The other terms, the negative 6x and the 7, those are going to have to move to the other side. Don't forget that they change sign. Also, don't forget whatever you add to one side, you have to add to the other. So this will be the first step to move in the direction of standard form. Next, we need to complete the square. Half of negative 8 is negative 4. Negative 4 squared is 16. And we're going to add that to both sides. Next, now that we have our perfect square trinomial, we know that that's going to factor as, well, a perfect square. We're going to have y minus 4. That's how that's going to factor. On the other side, we're going to have 6x, and I need to combine like terms. 16 minus 7 is 9. And then the next step to get to standard form would be to factor out a 6. We're going to have to factor the 6 out to remove the coefficient of x. So what is 6 factored out of 9? Well, we're going to have to go over and divide. 9 divided by 6 is 3 halves. So that's going to be plus 3 halves in the parentheses. Now that we have our equation in standard form, we're going to need to determine the values for h, k, and p. So I'm going to copy down the formula, remember, in that first column of information, and then I'm going to circle to find values. So first, if I circle here, that's going to say negative k is negative 4. Changing the sign on both sides will tell me that k is 4. Again, if I circle up and down here, that's going to say that negative h is 3 halves. Changing the signs on both sides gives me h is negative 3 halves. And again, circling up and down here says that 4p has to be 6. Dividing both sides by 4 gives me that p is 3 halves. And so these values need to be reduced to lowest terms. And now that we have h, k, and p, we can find pretty much anything we need. Let's start with the easiest piece. The vertex is the ordered pair h comma k, which in this case will be negative 3 halves comma 4. The focus in our information sheet says that it will be the ordered pair h plus p comma k. So plugging into that formula, h is negative 3 halves plus p is 3 halves comma k. And simplifying, I don't know if you noticed that, those are going to cancel and give me 0 comma 4. So there's our focus. Next, our directrix. Going back to our information sheet, the directrix is x equals h minus p. So plugging in, we're going to have x equals h minus p. And I need to combine like terms. A negative 3 halves and a negative 3 halves is a negative 6 halves. But negative 6 divided by 2 is negative 3. So there is our directrix. The axis of symmetry from the information sheet is y equals k. So that's going to give us an axis of symmetry of y equals 4. Now, one other thing we can find, since we know p is positive, according to our information sheet, if p is bigger than 0, it will open right. And let's also find the endpoints of the latus rectum just for fun. So if I could sketch just a basic graph here, knowing that the focus has to be inside the parabola, here our latus rectum points are going to be at the same x coordinate as the focus. Do you see that? The latus rectum going perpendicular to the axis of symmetry that contain the focus, if it opens to the right, would have to have the same x coordinates as the focus. So our focus had an x coordinate of 0. So we want to come back to our equation in standard form and replace x with 0 and solve for y. All right, so here we have our standard form of the equation of the parabola with x replaced with 0. And now we're going to solve for y to get our latus rectum endpoints. So 0 plus 3/2, well, that's just 3/2. 2 goes into 6 3 times. 3 times 3 is 9. And so that'll give us y minus 4 squared equals 9. When I simplify this side, taking the square root of both sides is going to give us y minus 4 equals, don't forget your plus or minus, 3. And one more step, bringing the minus 4 over will give us y coordinates of 4 plus 3 and 4 minus 3. And so then we can determine the endpoints of the latus rectum. Remember, the x coordinate was 0, so that's going to be at 0, 1, doing this arithmetic, and at 0, 7. And I think what I'd like to do is go to DESMOS and verify all of this information. And to check our second example in DESMOS, here I have input the equation they gave me in general form. The first thing I want to check is make sure that I converted to standard form correctly. So if this standard form is correct, it should give the same graph as the general form. So if I turn that on and off, can you see that that is the same graph? They're laying on top of each other. Next, the vertex should be at the center point of the parabola, which it is. The focus is inside the parabola. So here I've got my directrix. Notice the parabola opens away from the directrix and encloses the focus. And the distance from the vertex to the directrix is the same as from the vertex to the focus. Next, the axis of symmetry going through the focus vertex perpendicular to the directrix. And then the last thing I wanted to check were the endpoints of the latus rectum. So if I turn those on, you can see that they are on the parabola as they should be. And if I connect the dots across, notice it contains the focus perpendicular to the axis of symmetry and parallel to the directrix. And so everything checks out visually in DESMOS. In our next example, we're going to look at a situation where you're given certain information about the parabola, and they're going to ask you to write the equation of the parabola. So here we're given the focus and the vertex. What you want to do in this case is determine which coordinates are identical. So in this case, we can see that we have the x coordinates that are identical, and that will determine whether we have a vertical or a horizontal axis of symmetry. So back to our information sheet, notice that in the vertical axis, the x coordinates for the focus and the vertex are both h. That indicates that the x coordinates would have to be the same, and so then that tells us that we have a vertical axis of symmetry, and we're going to be using all of these formulas. In other words, all of these formulas apply to our problem. Now, the information that we're able to gather first from the vertex, we know that the ordered pair is h comma k, and so that will indicate that the value of h is -2 and the value of k is 4. From the focus, we can determine the value of p. So notice that h is negative 2, so I can't get anything new from the x-coordinate of the focus, but the y-coordinate of the focus is k plus p, which in our case, that value is 0, and we know that k is 4. So then if I replace k with 4, I can solve for p. Moving the 4 over gives us a p-value of negative 4. And then once I know h, k, and p, I can write the standard form of the equation of the parabola. Again, we're using the vertical axis, so that's going to be x minus h squared equals 4p y minus k, and then doing a little plug and play. H is negative 2. So x, listen, minus a negative will make that a plus 2 squared equals 4 times p. P is negative 4. Y minus k. K is 4. So that's just going to be y minus 4. And then I need to simplify doing the multiplication. So my final answer, in standard form, x plus 2 squared equals negative 16 y minus 4. And that should be our equation in standard form. Now, if you needed this in general form, what you would do is you would need to FOIL this set of parentheses. You would need to distribute the negative 16 and then move all of those terms over to make it equal to 0. So I'm not going to do that. That's pretty straightforward, but you would need to multiply all of this out and set it equal to 0 in order to get to general form. All right, in our next example here, we're going to be given the focus and the directrix. Again, they want me to write the equation of the parabola. So the first thing you're going to have to do is identify whether you have a vertical or horizontal axis of symmetry. In this case, it should be pretty easy since we are given the directrix. It is x equal a number. And if we go back to our information chart, you can see that the only column that has x equal as a directrix is the horizontal axis of symmetry. And so here all of these formulas apply in this example. All right, so I've written down the formulas for the focus and the directrix. Wanted to point out that since k is all by itself as the y-coordinate of the focus, that will indicate that k is negative 3, and that's one of our 3 variables found. Next, notice that h plus p should correspond to a value of negative 7, and h minus p should correspond to a value of 1. So we're going to use our knowledge of solving systems of linear equations to find h and p. So to set up our first equation, we know that h plus p has to be negative 7, and we know that h minus p has to be 1. And we're going to be able to use the addition method to solve for h. Adding, we're going to get 2h. The p's cancel. Negative 7 plus 1 is negative 6. Dividing both sides by 2 gives me an h value of negative 3. And then if I bring that back up and substitute, that will tell me negative 3 plus p is negative 7. Adding 3 to both sides should give me p. Negative 7 plus 3, that's negative 4. And now we have h, k, and p. Remember, k is negative 3. Once you know all 3 of those values, you can find your equation in standard form. So this time, since we had a horizontal axis of symmetry, we know that our equation is going to be y minus k squared equals 4p x minus h, and then doing a little plug and play. That's going to be y minus, now careful, k is negative 3, so minus a negative makes that a plus 3 squared equals 4 times p, which is negative 4, x minus, careful again, h is negative 3, minus a negative makes it a plus. And then simplifying, we're going to get y plus 3 squared equals negative 16 x plus 3. And that would be the equation in standard form. And for our last example, I thought it might be interesting to explore a situation where you're given information about the parabola and asked to find the equation, but you're not actually given enough information. So let me explain what I mean. Here we have the vertex given to be 4, negative 3, which I have plotted over here on the graph, and we are given one of the endpoints of the latus rectum. Now remember, the endpoints of the latus rectum have to be points on the graph. Now the reason that this is not enough information to determine the equation of the parabola is because in this situation you could have a parabola that opens to the right. So here we have the vertex, and remember the latus rectum has to go from side to side and contain the focus. So this could be a situation where the parabola opens to the right, but we could also have the situation where the parabola would open up. And again, this endpoint of the latus rectum, it would be a point on the parabola and contain the focus, but in this case it opens up. And so in order to determine the equation of this parabola with this given criteria, you're going to need one more piece of information, and that is the direction that the parabola opens. So here, let's say that we are also given the information that the parabola opens right. And so now we have enough information to actually find the equation given the vertex and an endpoint of the latus rectum, knowing that it does open right. Okay, so what do we know? In either case, remember, if it opens up, down, or left and right, the vertex is the ordered pair h comma k. And so right off the bat, we know the values of h and k. The other piece of the puzzle that I need is p. I need the value for p. So if you remember, the latus rectum is just going to be a point on the graph, and so I'm going to say that that's just a generic x comma y, but it is on the parabola. And what do we know from our information sheet? Well, if the parabola opens right, then we know that our standard form is going to be this formula here. So the next thing to do is to write down the standard form of the equation of our parabola. Y minus k equals 4p x minus h, and we have enough information to substitute and solve for p. So the y is going to be this value of y from the point on the graph minus k, see k is minus 3, and minus a negative makes it a positive, equals 4p, I don't know p, but x comes from the generic point on the graph, minus h is 4, and now I can solve for p. 0 plus 3, that's going to be 3 squared, which is 9, equals 4p. 6 minus 4 is 2. And then 2 times 4 is 8. So that'll be 9 equals 8p. P. Dividing both sides by 8 tells me P is 9/8. And now I can go back to my standard form and write the equation of my parabola. So that's going to give me y minus k, again minus a negative makes it a plus, 3, quantity squared, equals 4p x minus h, which is x minus 4. And then I need to simplify this multiplication here. So my final answer is y plus 3 squared equals 4 goes into 8 2 times. That'll be 9/2 x minus 4. And we're done. And that's going to do it for this particular lesson. So if you have any questions or comments about anything covered in this video, please feel free to leave those in the comment section below, or you can text me. And thanks for watching.